Hello students, in this lecture we will solve some problems related to JFET. So before going to solve some problems on JFET, I will recall the N-channel JFET. N-channel JFET is shown with a symbol. You can see the gate current is shown inward direction and drain current is downward direction, source current is in upward direction. We can apply the VDD as a source required for the flow of current from drain to source, and VGG is the voltage applied across gate and source to regulate the flow of majority charge carrier from source to drain. So this is the standard topology of connecting a n-channel JFET. So JFET characteristics. So basically three different types of characteristics we need to take into consideration. First is the drain characteristics ID versus VDS for a change in at a constant VGS. You can see as you keep on increasing the VDS, ID is increasing. Okay, and this region is called as a ohmic region. Whenever the VDS is less than minus VP, remember VP is a negative value. So for example, you take VP is minus 3, minus VP minus of minus 3 is 3. So when VDS is less than 3 volts, the JFET acts like a ohmic or resistor, linear resistor. Therefore, as voltage increases, current is linearly increases. Once VDS reaches the pinch of voltage, the channel will become very narrower. After that, even though you increase the VDS, the IDS will not further increase. That means ID or drain to source current is being saturated. So even though VDS is being increased after minus VP or pinch of voltage, ID is constant. It is called IDSS or saturation mode of current. So when the JFET is operating in between minus VP and BVDS, it is called active mode of operation or saturation mode of operation. When VDS is greater than breakdown voltage, obviously the reverse bias junctions will break down, which lead to rise in the electrical current because of breakdown of potential barrier between P and N junctions. So whenever your VDS is less than minus VP, it will be operating in ohmic region. Whenever the VDS is greater than VP, it will be operating in saturation region or active region. Now we will see in this figure the drain current characteristics ID versus VDS for different values of VGS. For different values of VGS. Previously, we have seen for only one value where VGS is equal to 0. So when VGS is equal to 0, like previous drain current characteristics, as VDS increases, ID keeps on increasing until unless VDS is equal to minus VP. So once the VDS reaches the pinch of voltage, when the VDS is greater than pinch of voltage, automatically ID got saturated, and we will ensure that our VDS is not greater than breakdown voltage of VDSs. So these first characteristics are similar to the characteristics which we have seen in the last slide, where VGS is equal to 0. The drain current required, the VDS required for the gate to go into saturation region is 3 volts. You can see when VGS is equal to 0, at 3 volts, the JFET is moving from ohmic region to saturation region. Now what I will do is that I will increase the reverse bias between gate and source. How we can increase the reverse bias between gate and source in a N-channel JFET? You apply a negative voltage between gate to source. Now VGS is equal to minus 1 volt. So because of this VGS is equal to minus 1 volt, the drain to source voltage required to make the JFET go from ohmic region to saturation region will be decreased by 1 volt, because what is the borderline equation? The borderline equation is VDS is equal to VGS minus VP. When VGS is equal to 0, VDS is equal to 3 volts. Now when VGS is equal to 1 volt, minus 1 volt, sorry, minus 1 volt, minus 1 plus of plus 3. So when VDS is equal to 2, it will move from ohmic region to saturation region. Next characteristics, when VGS is equal to minus 2 volts. When VGS is equal to minus 2 volts, the amount of VDS required for the JFET to move from ohmic region to saturation region will further decrease, taking into consideration VDS is equal to VGS minus VP. VGS is minus 2 plus 3, 1 volt. When VDS is equal to 1 volt, it will go from ohmic region to saturation region. When VGS is equal to minus 3 volts, that means VGS itself is equal to pinch off voltage, then drain current will become 0, because when VGS is equal to VP, automatically the channel will be completely closed because of reverse bias applied between gate and source. These VGS, when VGS is equal to VP, ID is equal to 0, can be depicted in transfer characteristics. This is called transfer characteristics. Now VGS should be, when VGS is equal to 0 and at a given value of VDS, it is a maximum current IDSS. What is the maximum current for any given VDS value? This IDSS is the maximum current. As you increase the VGS in negative direction, VGS is equal to minus 1, minus 2, and VGS is equal to minus 3. Pinch of voltage is minus 3. Once the VGS reaches pinch of voltage, ID will become 0. In other cases, maximum value of ID for a VGS is equal to 0 is ID is equal to IDSS. So when the JFET is operating in saturation region, ID is equal to IDSS into 1 minus VGS by VP whole square. So this is the pinch off voltage. That is pinch off voltage is minus 3 volts. And what is ohmic region? When your drain to source voltage is less than VGS minus VP, the JFET is operating in ohmic region. When VDS is greater than VGS minus VP, the transistor is operating in active region or saturation region. So this is the basic condition for finding out or assuming whether the transistor is operating in ohmic region or transistor is operating in active region. So before going to the problems, let us recall the equations which are required for solving the problems of JFET. So when the JFET is in ohmic region, the drain current is given by, it is not going into active mode, it is still operating in ohmic region. The drain current is given by IDSS into 2 into 1 minus VGS by VP, VDS by minus VP minus VDS by VP whole square. For small values of VDS, it will behave like a linear resistance. So the linear resistance RD is equal to VDS by RD, where we will think that VDSS is very much smaller compared to VP. So then RDS is equal to VDS by ID, which is equal to VP whole square by 2 IDSS into VGS minus VP. This is the formula which is used with the assumption that VDS is very small compared to VP. So when the JFET is operating in active region, what is the condition for JFET to operate in active region? VDS should be greater than VGS minus VP. If VDS is less than VGS minus VP, it is operating in ohmic region. So what is the borderline equation? VDS is equal to VGS minus VP. So when JFET is operating in active region, ID is equal to saturation current or saturated drain source current IDSS into 1 minus VGS by VP whole square. So let us solve the first problem. I will explain step by step. The students can take pen and paper and solve it by your own before each and every step. So let us take one problem. Figure shows a JFET which is being connected to 18 volts. This VDD is redrawn it as plus VDD. So plus to minus VDD, it is connected to VDD is 18 volts and it is connected to BDS, drain to source, through RD resistance. RD is 500 ohms. So current will flow from VDD through RD and plus VDS. Whereas no VGG is equal to 0, in simple, the gate and source are short circuited. As gate and source are short circuited, VGS is equal to 0. So what is the given parameters? He has given drain to source saturated current is 8 milliamperes. So IDSS is 8 milliamperes. Pinch off voltage is minus 4 volts. He has asked to calculate ID and VDS and verify whether it is operating in active region. So there is two formulas for ID. One is based upon your circuit equation. One formula is based upon assuming whether the JFET is operating in active region or ohmic region. So first we are going to write first equation applying KVL to the right hand side loop, as we have done for a BJT, applying KVL to the right hand side loop. How we can write the equation? You can write in either ways. Minus 18 plus IDRD plus VDS is equal to 0, or we can write down 18 volts is equal to IDRD plus VDS is equal to 0. Since VGS is equal to since the gate and source are short circuited, VGS is equal to 0. So we once we'll apply the KVL to this loop, we can write a equation VDD is equal to IDRD plus VDS, right? Or else we can say minus VDD plus IDRD plus VDS is equal to 0. Reassembling, you will get the same equation. Substituting the values in the equation, VDD is 18 volts. ID we need to determine. RD is equal to 500 ohms given in the problem. We are writing VDS. There are two unknowns. We don't know ID, we don't know VDS. We can reframe this equation and write down ID is equal to 18 minus VDS by 500. So ID is equal to 18 minus VDS by 500. We can once again simplify this equation. So this is the first equation which we got in terms of circuit equation. Second equation we'll write based upon the characteristics. That means let us assume JFET is operating in active region. Let us assume JFET is operating in active region. That means VDS is greater than VGS minus VP. Okay, when it is in active region, what is the formula? ID is equal to IDSS into 1 minus VGS by VP whole square. We have to use this formula. Now substituting IDSS given in the problem 8 milliamperes into 1 minus VGS is 0. So ID is equal to IDSS, obviously, because VGS is equal to 0. You got 8 milliamperes. Now we got ID value. Assuming the transistor is in operating region, we'll substitute this ID value in the previous equation. What was the previous equation from the KVL? 18 is equal to 8 milliamperes into 500 plus VDS. So this is the equation. 18 is equal to VDD is equal to ID RD plus VDS. I'm using the circuit equation and substituting this ID in this equation. What we got, VDS is equal to 14 volts. So there the problem does not end. So we have to cross check whether our assumption that JFET is operating in active region is correct or not. So what is the condition for JFET operating in active region? VDS should be greater than VGS minus VP. So what is VGS here? 0. So VDS should be greater than minus VP. What is the VP value given in the problem? 4 volts. So 14 is greater than 4 volts. That is the thing. So we have to verify whether our assumption is correct or not. So VDS should be greater than VGS minus VP. VGS is 14 volts. VGS is 0, VP is 4 volts, minus 4 volts. So 14 is greater than 4. Assumption is correct. There ends your first problem. So we determine ID as 8 milliamperes and VDS as 14 volts, and JFET is operating in active region. So second problem is very much similar to the first problem. What we are going to do is that we'll increase the drain resistance from 500 ohms to 2 kilo ohms. Let us see whether the JFET still operates in active region or ohmic region. So my second problem is similar to first problem. For the given JFET circuit shown below, the IDSS is 8 milliamperes, pinch off voltage is minus 4 volts. If RD is 2000 volts, verify whether the circuit is still operating in active region or ohmic region. So what is the first thing what we have to do is that let us assume transistor is operating in active region. As JFET is operating in active region, then ID is equal to IDSS minus VGS minus VP, what we had done similar to the previous problem. So ID is equal to 8 milliamperes. Now we have to substitute this 8 milliamperes in this circuit equation. What is the circuit equation? VDD minus VDD plus IDRD plus VDS is equal to 0, or VDD is equal to IDRD plus VDS. So in other words, ID is equal to 18 minus, using nodal analysis. Let us think. ID is equal to 18 minus VDS by 2000. So ID is equal to 18 minus 2000 VDS by 2000. Substituting, we got VDS is equal to 2 volts. Now VDS is equal to 2 volts. We have to check whether my assumption that JFET is operating in active region is correct or not. What is the condition? VDS should be greater than VGS minus VP. Substituting, 2 is greater than 4. It is false. 2 is not greater than 4. So JFET is assuming that JFET operating in active region using this formula is incorrect. So JFET is not operating in active region. It is operating in ohmic region. So we cannot use this formula. We have to use the ID formula when the JFET is operating in active region. So the ID formula for JFET operating in ohmic region is IDSS 2 into 1 minus VGS by VP into VDS by minus VP minus VDS by VP whole square. Substituting, the VGS is equal to 0, VP is equal to 4, your IDSS is equal to 8 milliamperes, which has been given in the problem. Saturation drain current is 8 milliamperes. After that, if you simplify this, you will get 4 4 into 10 power minus 3 VDS minus 0.5 into 10 power minus 3 VDS square. You can simplify this equation by taking pen and paper by yourself. The other equation for ID is from the circuit. So ID is equal to, using nodal analysis, 18 minus VDS by 2000. We can use that 18 minus VDS by 2000. So 18 by 2000, 9 milliamperes minus VDS by 2000. So now we have two equations for ID. Okay. Can we equate the right hand side equations? Yes, we can equate. So equating these two equations, this and simplifying it. So taking this equation on the left hand side, 9 minus 0.5 VDS into 10 power minus 3 is equal to 4 VDS minus 0.5 VDS square into 10 power minus 3, which is missing in my presentation. 10 power minus 3, 10 power minus 3 with kit cancel. This will result into quadratic equation VDS square minus 9 VDS plus 18. Once you simplify this quadratic equation, we'll get two values of VDS. The two values of VDS I got is 3 or 6 volts. We can consider both the voltages. Let us take first case, VDS is equal to 3. So what we have assumed, that transistor or JFET is operating in ohmic region. So the condition for JFET operating in ohmic region is VDS should be less than VGS minus VP. If you take 3 on the left hand side, 0 minus of minus 4. So this, once you select this value, it is satisfying. So VDS is equal to 3 volts is the correct option. Whereas you take a second option, if you substitute 6, 6 is not less than minus 4. So this option is incorrect. This option is correct. So now I got VDS. Using the VDS in a circuit equation, I can find out ID. So ID is equal to 18 minus VDS by ID. So 18 minus VDS 3 volts by RD 2000, we got 7.5 milliamperes. So in this way we can solve the problems. Either we will give RD value, for different values of RD we need to find out ID and VDS. So basic steps is that, first write down the circuit equation, write down the equation from the characteristics, assuming whether the JFET is in active region or omic region. Once you got the values of VDS, substitute in the condition and check whether our assumption is correct or wrong. If our assumption is wrong, change the ID equation from assumption from omic region to active region. So I am giving an assignment for you students. So it is a almost similar problem. Instead of giving RD value, I am asking you to find out the RD value. For IDSS is equal to 8 milliamperes, VP is equal to minus 4 volts. Calculate the RD for which JFET operate in border of active and omic region. So whether I am clearly saying it is not operating in omic region, not operating in active region. So I have given a hint. So what is the border equation? VDS is equal to VGS minus VP. We have to use this condition and solve this problem. Wish you all the best.